topic is going to be on the design of reinforced soil walls. Basically, we will have an overview of earth retaining structures because reinforced soil walls is a particular type of earth retaining structure. So first, we'll have a look at which are the different type of earth retaining structures, then look at the various components, and then the design principles. I have tried to cover the fundamental principles, but it's not a complete, because of the limitation of time, I'm not going to cover each and every aspect, but I've tried to cover the most important aspects. Now, an overview of earth retaining structures. Now, if we look at imagine a vertical fill or a cut in soil. If you look at a wedge, actually, if you try to analyze the equilibrium of this wedge, if you try a free body, and if you recall the principles of applied mechanics, we can draw the force polygon. And you will find that, we know, if the wedge is in equilibrium, then the polygon has to close, actually. But if you calculate what are the forces, we have the vertical weight of this wedge, plus any surcharge if it is there, then the reactions on this, which can be resolved into a normal component and a tangential component, and we draw the forces, we find it doesn't close, which means this is not in equilibrium. And our experience shows, if you try to do something like this, it's bound to collapse. Now, to keep it in equilibrium, we have to supply a component, a horizontal component. And in the earth retaining structures, we are doing this. We are actually supplying that horizontal component, which keeps the wedge in equilibrium. And we can do it in two ways. One, we can provide the force from the outside by building a retaining wall, what we call a conventional or externally stabilized system, like that. Like any type of retaining wall, we are supplying this force from the outside. That's why we call externally stabilized. There is another way, we can also provide the equilibrium force internally. So these are called internally stabilized retaining wall systems. Now, which are the externally stabilized? We have mass gravity, then RCC, embedded walls. Then the internally stabilized, we have reinforced soil, anchored earth, soil nail walls, and tie back. And there are also something known as mixed systems, which can be partly external and partly internal. A good example is a anchored sheet pile. Now, look at the mass gravity. This can be PCC or masonry, gabion, crib walls. These depend on the pure weight, actually. That's why called mass gravity. It depends on its own weight to resist the earth pressures. Then we have the RCC, which is cantilever, counterfort, and buttress. We are familiar with these systems. Then another is embedded retaining walls. Here, these are relatively slender structure. The weight is very less. So it depends on the passive resistance mobilized in the embedded portion to resist the earth pressure. Plus, it will be subjected to bending. So sheet piles, diaphragm walls, then board pile walls, like secant pile, tangent piles. These are all examples of embedded walls. And these are usually most commonly used to retain cuts. Then coming to the internally stabilized systems, we have the reinforced soil walls. This will be more detailed later. Then we have anchored earth. The difference is the reinforced soil walls, the reinforcement mobilizes a lot of friction, whereas in the anchored earth, these consist of small diameter rods or strips, which mobilize very little friction, actually. So to mobilize the pull out, they need anchors at the end, which mobilize passive resistance. Then we have soil nail walls, which are basically, we are inserting the reinforcement into the existing ground. So mostly to stabilize an existing slope or to make an excavation. Also, we have something known as tie-back retaining walls. So these tie-backs, again, it is similar to soil nails. This these tie-backs are inserted into the existing ground. Only difference is the soil nails are passive systems. That means tension is mobilized only if the soil deforms, actually. Whereas these tie-backs, most commonly it is pre-stressed. That means you drill So insert the reinforcement, then you grout it, then pre-stress it. That means even before the ground deforms, it's in tension like that. So now if we compare reinforced soil walls versus anchored earth, there are a lot of similarities, but some differences. Like, see, both are used to retain fill. Like when we are doing fill, we can use reinforced soil or anchored earth structures. Then reinforcement is placed between lifts of fill actually. Here we can use metallic and geosynthetic reinforcement, whereas here it's mostly metallic only, either rods or strips like that. Then both cases, construction is from the bottom up because we are doing the filling. So it starts from the bottom, we proceed to the top. Then here, the difference is, in the case of reinforced soil structures, there is a good frictional interaction between the reinforcement and soil. So there is a very good composite action. Whereas in the case of anchored earth, the friction is limited actually. So we have to use anchors at the end which mobilize passive resistance. So this is the difference between these two. Now coming reinforced soil and soil nail wall. A reinforced soil wall is to retain fill, whereas soil nails to retain cut or stabilize existing slopes. Like if it is a cut, normally and again reinforcement is placed between lifts of fill, whereas here reinforcement is inserted into the existing ground. Like that means we first make a small excavation, then insert this nail, again excavate, insert this nail, like that. Then metallic and geosynthetic reinforcement can be used, whereas here it will be metallic only, normally a steel rod. Then another fundamental difference is here construction from bottom to up because we are doing filling, whereas here construction is from top down because mostly it is for cuts. And both are passive systems. Like for the reinforcement to mobilize tension, soil has to deform, then only it will mobilize tension. Same way here also. Like the soil nails, they are not pre-stressed. Only when you make an excavation, soil deforms, then only tension will be developed in the nail. So now, if you look at a problem of earth retention, we have to make either a fill or a cut. Like first, this is the first difference is, are we going to retain fill or are we going to retain cut? Like if it is fill slope, first we'll have to determine the safe slope angle. That means depending on the slope, so the height, the properties of the soil, properties of the foundation soil, there is a safe slope angle for that particular problem. Then we ask the question, can the available space accommodate this angle? Suppose we determine, okay, the slope is 30 degrees or 45 degrees. Do we have enough space to accommodate that? If the answer is yes, then this is the cheapest solution. We go for the slope, then we have to provide only erosion control. But if the answer is no, the space is very limited, then we'll have to go for some kind of earth retaining structure. And we have very different options. Like we have gravity retaining walls, which includes the RCC walls. Then we can go for a reinforced soil slopes or reinforced soil walls or a reinforced soil slope. These are the various options we have to evaluate each. Like each site, there is an optimum solution like that. Then coming to a cut slope, again we ask this question, determine the safe slope angle and do we have sufficient space? If there is enough space to have a stable slope, then we have to go for only slope with erosion control. But if the space is limited, then we have to go for either a breast walls, which is commonly used, especially in hill roads. See, breast wall is a specific rate of retaining wall in which there is no backfill. That means the retaining wall is put directly against the slope. Then we can go for embedded retaining walls, sheet piles, board piles, diaphragm walls, etc. Or we can go for soil nailing or like a tie-back wall or ground anchors. Like that. Now coming to the fill retention options. So these are the basic options. Like we can have a conventional retaining wall with a slope, provided some space is available. If there is absolutely no space, then we'll have to have a vertical wall to the full height actually. We can consider a reinforced soil retaining wall with a back slope, or we can go for a reinforced soil slope. Again, these are the available options. See now again, like it's not that we want to use a reinforced soil wall directly. We have all these options and we'll have to evaluate all the aspects, then pick up the most optimum solution. Now coming to the basic principles of reinforced soil structures, like a simple definition, like it's a composite earth structure, soil reinforced. Then this is an internally stabilized system, as you mentioned, like the wedge is trying to fail and we are going to stabilize it by reinforcing it internally. Then we have discrete layers of reinforcement and it is placed generally horizontally, like between successive levels of fill during construction. Like we have a reinforced soil structure. So normally if this angle with horizontal, if it is steeper than 70 degree, we call it a reinforced soil wall. If it is less than 70 degree, we call it a reinforced soil slope. And the 70 degree is somewhat arbitrary, like it could be 75, it could be 80, but most of the codes, they put the difference at 70 degree. Steeper than 70, we design it as a wall. Flatter than 70, we design it as a slope. And again, slope, again, it is classified into a steep slope and a shallow slope. If the inclination is 45 to 70 degree, it is a steep slope. And if it is flatter than 45 degrees, we call it a reinforced soil shallow slope. And these are the major differences. Like slopes, again, we will take it up tomorrow. Now let us look up what are the important components of a reinforced soil wall. Like we have the reinforcement, then the soil. So reinforcement plus the reinforced fill, that means the soil, the zone which is reinforced, it's called the reinforced fill. So together it becomes the reinforced soil structure. Then it has a facing. Then the reinforcement need to be connected to the facing, that means there is a connection. Then there is a leveling pad on which the facing panels or blocks have to be erected. There is a drainage layer like that. Then this is the structure now. Now this retains the earth. Like this is the retained fill. There is, and it is constructed on the ground, which is the foundation soil. Then there could be, like if it is a highway structure, there could be a crash barrier so that the vehicle does not fall over that. It may be supporting pavement. And it could be a bridge abutment also. In this case, it could be supporting the bridge deck directly. Now we look at the components one by one. First is the reinforcement. Now what is the function of the reinforcement? As we discussed earlier, the function is to supply that missing force, which will keep this wedge in equilibrium like that. So the sum of the reinforcement tensions should be equal to this active earth pressure. That's the basic principle. Now we have different types of reinforcement. Metallic, there are so many varieties. Then polymeric or geosynthetics, we have geotextiles, geogrids or polymeric straps. And our focus is going to be on the geosynthetic reinforcement. So different types of geogrids. This is the punched and oriented geogrids, one of the first geogrids to be developed, which are also mostly made of high density polyethylene, also called as stiff grids. Then we have woven or knitted and coated polyester geogrids. It's made of polyester filament yarn coated with PVC or other polymers. Another is laid and welded grid. Here we have strips of polyester which are welded by ultrasonic or laser welding. Another type is straps. These are like strips of typically 90 to 100 millimeters wide, again made of polyester filament yarns, and which has a polyethylene sheath to protect it like that. Another is we have a non-woven geotextile, which is reinforced with high tenacity polymer filament yarns in both directions. So mainly the strength is given by this filament yarns, whereas the non-woven geotextile does like something like a drainage. Like sometimes when we have poor quality soil, like silts or clays, like this is like a composite actually. This yarns gives the reinforcement. The non-woven geotextile acts as a drainage layer. Then the properties of reinforcement, one is the long-term design strength, because the reinforcement has to resist tension. So the tensile strength is a very important property. Another is it has to develop friction or bond with the soil. So same as like reinforced concrete, if you use a steel rebar, tensile strength and bond strength, these are the most important properties. Also, the reinforcement has to be connected to the facing. So connection strength is another important property. So whatever type of reinforcement like geotextiles, geogrid, strip, ultimately in design, these are the properties which we use. Coming to the facing, like what is the function of the facing? Basically, this is the structure actually, the soil and the reinforcement. This is the actual structure. So why do we need a facing actually? So one is like imagine the facing was not there. Will we be able to construct the reinforced soil wall? That means we have to place the reinforcement, we have put the soil and compact it. And if you don't have this facing, it's very difficult to compact. Like imagine the soil is vertical, the roller comes to the very close to the edge, we'll not be able to compact it. For the fill to be compacted, it has to be confined. So one function is, it is like a formwork to contain the fill during compaction. Just like if you have a beam, like to pour the concrete, we have to have a formwork like that. Once the concrete hardens, that's not required. It's a purely temporary. Same way here, one is sort of a, just during construction, the role is there. Second is like if, okay, it is constructed and we know the reinforcement develop tension, it keeps in equilibrium. But with time, we know some of the soil will erode, like during rain, or sometimes it can ravel off like that. So without a facing, it's not going to survive for long actually. So gradually this will erode and then finally it will fail. Third is to anchor the reinforcement. To understand this I have plotted the tension, how the tension varies along the reinforcement. Like it's not constant along its length. See, where this critical failure plane intersects, the maximum tension develops. Then to this side, it reduces. Again, to this side, it reduces. So if we recall the concept of development length in reinforced concrete, like where the tension is maximum in the reinforcement, to either side, it should have enough length, enough bond length. Then only the tension can be resisted. Same way here, like we need bond length this side. We also sometimes we don't realize we need enough bond length this side also. So then only it can hold this wedge in equilibrium. So suppose like many times, especially in the lower portion, this bond length may not be sufficient. So here the facing role is important. That means the facing resists the air pressure and distributes it back into the reinforcement. So this is what we call like to anchor the reinforcement. So another way is to have a wraparound facing, like that also will help. Then third is to protect the reinforcement, because if the reinforcement is exposed, it can be damaged. And last is aesthetics, like the structure should be safe, at the same time it should look good also. Then we have different types of facing, like we have full height panels. That means one panel to the full height of the structure. So we have incremental panels or discrete panels, which is a very popular type of facing. Like how it looks. We can have different shapes. Then we have small concrete blocks actually. So these are like panels need heavy like crane to be lifted. Like even the incremental panel weighs about a ton like that. So these are small blocks which weighs about 30 or 45 kg, which can be lifted by a person placed manually. Again, this can be hollow, solid. We can also have large blocks actually. Then different types of blocks and how the reinforcement is placed. We can have like previously this is what we call a frictional connection. So that means there is no mechanical fixture between the block and the reinforcement. This works just by friction. Like we have the reinforcement and the block is just placed over that. So only because of the friction that connection is developed. But we can also have what is known as a positive connection. So there are fixtures which gives something like a mechanical connection. We can have a welded wire mesh, which is bent to a L shape, then with these struts, then the geogrid goes up and goes back. Like near about say 1 meter, we can have this type of facing, and we can have either vegetation or we can have stone. Like in certain climate, because vegetation is not possible everywhere, like we need a favorable climate, rainfall to sustain vegetation. So if that is not there, we can go with stone actually. Like we place stone behind the face like that. Then we can have geocells. These are the type of geocells. Like same way like blocks, we can stack geocells and geogrids goes in between. We can have vegetation, or we can place stone, or even sometimes even concrete also. Then we can also have gabions. That is another. So like sometimes we say facing, like it's not a structural element. Actually the reinforcement plus soil, that is actually the structure. The facing is just like a skin, but still it is very important. One, like it performs several functions, important functions. Then most of the construction problems are due to the facing actually, because the placing geogrids is very easy, placing fill is very easy, mechanized compaction, but actually the placing the facing to the correct line and level, it is a tricky part actually. So most of the construction problems will have to do with the facing. Then the quality of the finished wall will usually be judged by the quality of facing, because once the wall is complete, we never get to see the soil. We don't see the reinforcement. What we see is the facing. So if the facing is good, we say it's a good wall. But if the facing is bad, like we are not happy with that wall. Then another is the cost of facing may be typically like 40 to 50%. Like the cost of reinforcement varies as the height increases, but the cost of facing is normally fixed, like per square meter. So as the wall height increases, the cost of facing, that proportion goes down. But typically low height walls, say 6 to 8 meters height, it can be up to 40 to 50% of the overall cost. Then another important aspect is the allowable settlement. Like the reinforced soil, it's flexible, it's made of earth, it can accommodate a lot of settlement. But the facing, if it is, especially if it is a full height panel or a block, it can, there is a limit to which settlement. So the allowable settlement for a reinforced soil wall will be normally decided by the type of facing. Again, so that is an important design criteria. Then the reinforcement has to be connected to the facing. And this is done in several ways. If it's a panel, there are like a steel hooks embedded. There could be a strip or a bar. Then the geogrid is wrapped around. There are different systems have different connections, but connection has to be there. Like if it is block, we can have a purely frictional connection, or we can have a mechanical connection. Like both, provided it's designed. Then why is connection important? Like, see, first of all, like the facing is a very slender element. So the reinforced soil wall may survive, but if you don't have a connection, like imagine that if it is a panel, the thickness is just 160, 180 mm. If it is a block, maybe 200 to 300 mm like that. And imagine a 10-meter high wall. This is a very slender structure. So unless it is connected to the facing, it will not be stable. Secondly, like suppose the fill settles. Like sometimes if the fill is not properly compacted, so due to the weight of the overlying fill, it can undergo some settlement. So that reinforcement get pulled out like that. So both ways we need a proper connection between the facing and the reinforcement.